Take a coin. Hold it between your fingers. Now flip it. While it's spinning in the air, is it heads or tails? Classical physics says it's one or the other. The trajectory is determined by the initial force, the angle, the air resistance. In principle, if you had perfect information about all of that, you could calculate the outcome before it lands. Your uncertainty is ignorance. The coin has a definite answer. You just don't know it yet. Now take a quantum particle. Put it in what physicists call a superposition. Ask the same question. Is it this state or that state? Quantum mechanics says it's not one or the other. Both possibilities exist simultaneously, not as uncertainty about what's really there, not as probability standing in for ignorance, as physical reality. Both states are real at the same time in the same particle. The difference between those two cases, between classical uncertainty and quantum superposition, is the deepest conceptual divide in the history of physics. And understanding that difference is everything. Let's be careful, because this distinction sounds philosophical, but has hard experimental consequences. In classical physics, systems always have definite states. A particle has a definite position, a definite velocity, a definite spin. You might not know those values. Your measuring instruments might disturb them, but the values exist. Uncertainty is always epistemic. It's always about your knowledge, not about reality. Quantum mechanics makes a different claim. It says that before measurement, a quantum system genuinely does not have definite values for certain properties. The uncertainty isn't in your knowledge, it's in the system. And here's how you know it's not just ignorance, interference. The double-slit experiment. Fire a single electron at a barrier with two slits. On the other side, a detector screen records where it lands. Do this many times. The pattern that builds up is an interference pattern, alternating bands of high and low probability, exactly the pattern you'd get from a wave passing through both slits simultaneously and interfering with itself. A particle with a definite path through one slit cannot produce this pattern. The mathematics is unambiguous. If the electron really went through slit 1, just secretly without us knowing, the interference pattern cannot appear. Two separate streams of particles going through separate slits don't interfere. Waves do, because a wave is spread out, going through both simultaneously. The electron produces the interference pattern, which means it went through both slits at the same time, as a single particle. That's superposition. Both paths simultaneously interfering with each other, producing consequences that a definite path particle cannot. Now, try to detect which slit the electron goes through. Put a detector at the slits. The moment you measure the path, the interference pattern vanishes. You get two distinct bands, the pattern of particles with definite paths. The superposition collapses when you measure it. Before measurement, both paths real, interference visible. After measurement, one path, no interference. This isn't philosophy, it's an experiment you can run. The results are reproducible to extraordinary precision. The superposition is physically real, not an artifact of ignorance, and the measurement destroys it. Now let's get precise about what superposition actually is mathematically. Because the mathematics reveals why it's weirder than probability alone can capture. In quantum mechanics, the state of a particle is described by a wave function, a mathematical object that assigns a complex number, called an amplitude, to every possible state the particle could be in. For our quantum coin, let's say an electron with spin, which can be up or down, The wave function in superposition looks something like half amplitude for up, half amplitude for down. When you square the amplitudes, you get probabilities, 50% up, 50% down. So far it sounds like probability. Here's where it diverges. The amplitudes are complex numbers. They have phases as well as magnitudes. Two superpositions with identical probabilities but different phases behave completely differently. They interfere differently. They evolve differently. Classical probability has no concept of phase. Quantum amplitudes do. This is why interference exists and why it's a quantum signature. The interference pattern in the double-slit experiment comes from the phases of the amplitudes for the two paths, adding and cancelling, constructively in some places, destructively in others. You cannot reproduce this with classical probability, with statements like 50% chance it went left, 50% chance it went right. Classical probabilities don't interfere. Quantum amplitudes do. The wave function isn't a description of our ignorance about a definite state. It is the description of reality. That's the claim quantum mechanics makes, and every experiment we've run for 100 years confirms it. Now, Schrödinger's cat, because it comes up, and it usually gets explained wrong. Erwin Schrödinger proposed his cat thought experiment in 1935. He wasn't explaining superposition, he was mocking it. Here's what he was saying. Quantum mechanics tells us particles can be in superposition. Fine. But what if you couple a quantum system, a radioactive atom, in superposition of decayed and not decayed to a macroscopic device, a mechanism that kills a cat if the atom decays? Then the cat is in superposition of alive and dead. And Schrödinger found that absurd. He was using it as a reductio ad absurdum against the naive application of quantum mechanics to macroscopic scales. The thought experiment became pop science shorthand for "the cat is both alive and dead, how weird," which completely inverts the intent. Schrödinger was saying, this result is ridiculous. So something must be wrong with applying quantum mechanics this way. The real question his thought experiment points to, why don't we see macroscopic superpositions? The atom is in superposition. The cat, coupled to the atom, should be too. But we never observe a cat that's both alive and dead. Why not? The answer is decoherence, and it's important. Quantum superpositions are fragile. They survive as long as the quantum system is isolated, not interacting with its environment. For a single electron in a carefully controlled experiment, you can maintain superposition long enough to observe interference. For a cat or any macroscopic object, the system interacts with its environment constantly. Air molecules, photons, thermal fluctuations, billions of interactions per second. Each interaction entangles the quantum system with its environment, spreading the superposition across an enormous number of degrees of freedom. The interference terms, the parts of the wave function responsible for quantum effects, don't disappear. They become distributed across so many environmental degrees of freedom that they are, for all practical purposes, undetectable. This is decoherence. Decoherence happens almost instantaneously for macroscopic objects. The cat decoheres faster than any measurement could capture its alive-dead superposition. Not because the superposition is destroyed, but because the interference becomes completely unmeasurable. This explains why we don't see quantum effects in everyday life. Not because they don't apply, they do to everything. but because the environment constantly measures macroscopic systems, washing out the interference before we ever get to observe it. But decoherence doesn't fully solve the problem. It explains why interference disappears. It doesn't explain why, when you measure a quantum system, you get one specific outcome rather than another. That's the measurement problem, and it's unresolved. Before measurement, quantum system in superposition. Wave function describes multiple outcomes coexisting. After measurement, one definite outcome. Wave function has, in some sense, collapsed. What happened? This is the measurement problem. It's been debated for a century. It's still open. The Copenhagen interpretation, the oldest and most commonly taught, says, don't ask. The wave function collapse is a fundamental process. The quantum description applies before measurement. After measurement, you have a classical outcome. The question of what happens during is not meaningful. The many worlds interpretation says the wave function never collapses. Every measurement outcome occurs in branching parallel universes. You find yourself in one branch, but all branches are equally real. There's no collapse, just universal evolution of the wave function and splitting of observers. Pilot wave theory says particles always have definite positions and velocities. There's a real guiding wave, the wave function, that influences their motion. The apparent randomness comes from our ignorance of initial conditions, not from fundamental indeterminacy. The particle always goes through one slit. The wave goes through both and guides the particle to the right statistics. Each interpretation makes exactly the same predictions for every experiment we can run. There is currently no experiment that distinguishes between them. The choice is philosophical or pragmatic. Shut up and calculate is a real position held by working physicists. 100 years of quantum mechanics. The technology is extraordinary. The foundations are still debated. Both of those things are true simultaneously, a kind of superposition of its own. Superposition isn't just a philosophical puzzle, it's a resource, and right now engineers are building machines that exploit it directly. A classical bit is either 0 or 1. A qubit, a quantum bit, can be in superposition of 0 and 1 simultaneously. A quantum computer with n qubits can be in superposition of all 2 to the power of n possible states at once. This isn't just storing more information, it's computing with all states simultaneously. A quantum algorithm manipulates the entire superposition, using interference to amplify the probability of correct answers and suppress wrong ones, before the final measurement collapses the result to a single answer. Quantum cryptography uses superposition for unbreakable communication. If you try to intercept a quantum signal, measure it, you disturb the superposition detectably. Eavesdropping leaves a trace. It's guaranteed by physics, not by the difficulty of a mathematical problem. Quantum sensors exploit superposition to measure gravity, magnetic fields, and time with precision far beyond classical instruments. Atomic clocks, the most accurate timekeeping devices ever built, work by exploiting quantum superpositions of atomic states. Superposition isn't an interpretation issue when you're engineering with it. It's a real, exploitable property of matter at the quantum scale. The technology works because the physics is real. Now, what does superposition tell us about reality itself? Before measurement, a quantum particle doesn't have a definite spin. It's in superposition. The wave function is a complete description of its state, and that state doesn't include a definite answer to which spin. If the wave function is complete, and quantum mechanics says it is, then the particle genuinely doesn't have a spin before you measure it. Measurement doesn't reveal a pre-existing value. It participates in creating the outcome. Einstein refused this. God does not play dice, he said. He believed the indeterminacy signaled an incomplete theory, that hidden variables, unknown to us, determined the outcomes secretly. Our ignorance, not real indeterminacy. John Bell proved in 1964 that you could test this. Any local hidden variable theory, any theory in which particles carry secret predetermined answers, makes predictions that differ from quantum mechanics in certain experiments. The experiments were run. Quantum mechanics won. Local hidden variables are ruled out. The quantum randomness is not due to our ignorance of hidden facts, at least not facts that respect locality, the principle that influences can't travel faster than light. The universe at its fundamental level appears not to have definite answers to all questions until those questions are asked. Measurement isn't passive. It isn't just revealing what was already there. At the quantum level, it's part of how definite reality comes to be. Back to the coin, classical coin in the air, heads or tails, determined, just unknown to you. It has an answer. You don't know it yet. Quantum coin, genuinely both, simultaneously, until the moment of measurement. Not unknown, undecided. The answer doesn't exist yet. That difference, between not knowing and there being nothing to know, is the deepest conceptual shift in the history of physics, more radical than heliocentrism, more radical than evolution. It changes what we mean by reality at the most fundamental level. And the strange thing, the thing I find most remarkable, is that we can build computers out of it, sensors, cryptographic systems, technology that only works because matter genuinely exists in multiple states simultaneously. The coin isn't hiding its face. It hasn't decided yet. And we're building the future with that indecision.